We often hear these grand pronouncements, right? Like mathematics is the language of the universe, or, biology is life.
Mm-hmm.
And sometimes you get that sort of jokingly arrogant stance. It often gets pinned on some famous physicist, maybe Feynman, maybe someone else.
Right, the idea that while every scientist thinks their field is number one,
Physics actually is. It's kind of a fun bit of scientific rivalry.
it is. And interestingly, that specific quote, it seems it wasn't actually from a big Nobel name, but maybe someone just, fascinated by it all.
Huh. Well, that's slightly exaggerated thought. It's actually a perfect lead-in to what we're doing today.
Exactly. We're diving deep into the psa visnum physici, basically, the content and significance of physics.
Okay.
And our source material, it was originally put together for students, technical secondary school students. But honestly, the core ideas, they're super relevant for anyone just curious about how things work.
Totally agree. So our mission here is to really unpack physics. We want to look at where the name came from, check out all its different areas, understand the methods physicists use, and really show how physics connects to, well, pretty much everything humans do. Okay, so let's start right at the beginning. The word itself, physics.
Right. So the word physics, it goes way back, comes from the ancient Greek word physis.
Physis?
Yeah, physis. And it just meant nature. Simple as that.
Okay.
So originally, if you were called a physicos, you were basically anyone studying any part of the natural world.
Wait, any part. So like if you were studying rocks or plants or stars, you were a physicist.
Pretty much. Yeah, back then it was all under that one big umbrella. Think about those early thinkers trying to figure out everything from planets to plants. They were all students of physis.
Wow, that's a broad definition. So how did that change? I mean, that sounds kind of overwhelming.
Well, exactly. As human knowledge about nature just exploded, trying to keep it all under one heading became, let's say, impractical.
Right. Too much for one person.
Way too much. So naturally, things started to specialize. You saw distinct scientific fields begin to split off. That's how we got biology, chemistry, mineralogy, geology, astronomy. They all sort of branched out from that main physis trunk as we learned more.
That makes total sense. Specialization happens.
Yeah.
But it wasn't just the theoretical sciences, was it? Didn't practical fields also start using this knowledge?
Oh, absolutely. At the same time, you saw technical fields popping up that directly used this physical knowledge. Think about early electrotechnics, engineering. Even things like military technology have always relied heavily on understanding physical principles. People always want to use what they understand about nature.
Okay, so the field splits, knowledge grows. But here's something interesting. We tend to put these subjects in neat little boxes, right? Physics here, biology there.
Yeah, we do.
Chemistry over here. But the sources we looked at really emphasize that those lines are, well, much blurrier in reality.
That's such a crucial point. Yes, we categorize for teaching, for organizing research, but fundamentally, all these sciences, they're studying the same thing, nature.
Right.
It's not separate islands. It's more like one huge interconnected continent of knowledge, and the proof is really in all the interdisciplinary fields that have emerged.
Like what?
Well, think about geophysics using physics to understand the Earth, or biophysics, looking at the physics inside living things, astrophysics, the physics of space.
Okay.
And then you've got chemical physics, medical physics, even econophysics.
Whoa, hold on. Econophysics, that sounds unusual. What are physicists doing in economics?
It's actually a fantastic example of this interconnectedness.
Yeah.
Physicists started applying methods from their field, especially from statistical physics.
Which deals with lots of particles, probabilities.
Exactly. They applied those ideas to analyze economic systems like stock markets. And the fascinating part, there are cases where physicists using these models actually predicted the big global economic crisis a few years back.
Seriously?
Yeah.
They saw it coming using physics models.
Apparently so. Now, initially, a lot of economists were pretty skeptical, Maybe the physicists' models just offered a different perspective on the data, saw patterns others missed.
Wow. Okay, that really shows how different approaches can uncover things. So let's shift focus a bit, back to the core of physics itself. We have these really fundamental concepts: matter, space, and time. Or komota, prostoru, and chesu in the original source.
Let's start with komota, or matter. It's obviously foundational in physics. And it comes in two main forms.
Two forms, okay.
The first one is probably what you think of first. Latka, or substance. That's your solids, liquids, gases, plasma stuff you can generally touch or interact with directly.
Right, tangible stuff. What's the second form?
The second form is pole, or field. Think of it like an area of influence. It can exert a force without direct contact.
Ah, like gravity or magnetism.
Exactly. Electric fields, magnetic fields, gravitational fields, those are all forms of matter in the physics sense.
Huh. Okay, so a table and gravity are both matter. That's broader than the everyday definition.
It is, and the really key thing about both forms, substance, and field is that they're always in pohub, or motion.
Always moving.
Well, motion here means more than just moving from point A to point B. It covers any kind of change. Mechanical movement, sure, but also electrical changes, chemical reactions, vibrations.
So even atoms jiggling in a seemingly still object counts as motion.
Absolutely. And all this matter, in all its forms and states of motion, it exists within prostura chasu, space and time.
Seems obvious, but I guess it's fundamental.
It is fundamental. You can't describe any physical event or phenomenon without considering where it happens in space and when it happens in time. They're the stage, the framework for everything.
It's got it. The stage for reality. Now, just like physics branched out into other sciences, physics itself isn't just one thing, right? It's got its own internal branches.
Oh, definitely. The same thing happened within physics. As knowledge grew deeper and wider, it just had to specialize. You can think of the branches as different zoom lenses for looking at specific parts of the physical world.
Could you give us some examples, maybe ones people remember from school?
Sure. You've got mechanics, that's all about motion, forces, how things move, like cars or falling apples.
Newton's territory.
Right. Then there's the physics of specific states. Liquids, solids, gases, plasma, each behaves differently. Optics deals with light. Molecular physics looks at molecules. Then you get into bigger theories like the theory of the electromagnetic field,
Okay.
Einstein's theory of relativity, and of course the weird and wonderful world of quantum physics.
And that's just scratching the surface, I imagine.
Oh yeah, lots more specialized areas. It really is like a massive family tree of knowledge.
Okay, so speaking of big theories, our sources also talk about this split between classical and modern physics. What's the deal there?
Right, so classical physics is basically everything understood up to about the end of the 19th century. Think Newtonian mechanics, his laws of motion and gravity, and Maxwell's theory of electromagnetism, which brilliantly tied electricity and magnetism together.
The foundations, really.
Exactly. And these theories were, incredibly successful, explained so much for so long.
There's always a but, isn't there?
There usually is in science. The but was that classical physics started hitting walls. It couldn't properly explain certain things.
Like what kind of things?
Things happening at really, really high speeds, close to the speed of light, or things happening on the super tiny scale of atoms and subatomic particles. Classical rules just didn't work there.
Ah, okay. And that's where modern physics comes in.
Precisely. Early 20th century, boom, we get modern physics. Two huge pillars, Einstein's theory of relativity.
Space, time, gravity, the big picture.
Right. And quantum mechanics, developed by Schrödinger, Heisenberg, others, which describes how things behave at that tiny, fuzzy, probabilistic atomic level.
But, and this seems important, modern physics didn't just, throw out Newton, did it?
No, absolutely not. That's a really critical misunderstanding some people have. Modern physics expanded our understanding into these new extreme realms.
Okay.
It didn't make classical physics wrong within its own area of usefulness. For everyday objects, moving at normal speeds, classical physics works perfectly fine. You don't need quantum mechanics to figure out how to build a bridge.
Right tool for the right job, essentially. Makes sense. Okay, so we've talked about what physics studies. What about how physicists actually do their work? The methods?
Good question. Our sources point to three main ways, three interconnected methods. First, there's experimental physics.
The lab coats and equipment.
Kind of, yeah. These are the folks designing and running experiments, making careful observations. Their job is to test theories, see if they hold up against reality, and also sometimes to stumble upon new things that nobody can explain yet, which then sends the theorists scrambling.
Okay, providing the raw data, the evidence.
Exactly. Then you have theoretical physics.
The thinkers, the equation writers.
That's a fair way to put it. Theorists develop the new ideas, the mathematical models that try to describe why things work the way they do. They work with abstract concepts, complex math, and they often suggest new experiments to test their theories.
Got it. Theory and experiment feeding each other. What's the third one?
The third, and increasingly vital, is computational physics.
Using computers.
Right. Computers are now essential tools. They're used to process the huge amounts of data that come out of modern experiments.
Makes sense.
They're used to build simulations, models of situations that are too complex, too dangerous, or maybe even impossible to create in a lab. The source mentions modeling stuff falling into a black hole, for example.
Whoa, okay. You can't exactly run that experiment.
Not easily. And computers are also crucial for solving really complicated mathematical equations that describe physical systems equations that you just can't solve neatly with pen and paper. You know, in basic math, you follow steps, get an answer.
Add, subtract, divide, underline, like the old saying.
Exactly. But many physics equations are way messier. Computational methods let us get really good, approximate answers.
So experiment, theory, computation, all working together.
Absolutely. They're totally interconnected. Progress in one area almost always pushes the others forward. It's a cycle.
Okay, now one more way to categorize physics by its goal, almost.
Yeah.
Basic versus applied research. What's the difference?
Right. Basic research is really driven by curiosity. It's about understanding the universe at its most fundamental level.
Knowledge for knowledge's sake.
Sort of, yeah. The main aim is discovering new things, developing new theories, often without any immediate practical use in mind. But the key thing is, history shows these useless discoveries often lead to huge breakthroughs down the road, completely unexpectedly.
Like exploring uncharted territory. You don't know what treasures you'll find, but you explore anyway.
That's a great analogy. Then you have applied research that's much more focused on solving specific problems.
Practical problems, like industry stuff.
Often, yeah. Taking the physics we already know and using it to create new technologies, improve old ones, solve a particular challenge facing society or industry, the payoff is usually more immediate, more tangible.
Okay, so basic is the why. Applied is the how to use it. Got it. Now let's really hit that significance part of the topic. The sources give great examples of physics underpinning other fields. Let's start with medicine.
Oh, the impact of physics on medicine is just immense. It's everywhere. Think about optics. Simple eyeglasses rely on it.
Sure.
But so does complex laser eye surgery. And lasers themselves, which came out of quantum physics, are used in tons of procedures. The semiconductor laser development even won a Nobel Prize.
And X-rays. Everyone knows X-rays. Huge diagnostic tools.
Huge. And based on a physics discovery that actually won the very first Nobel Prize in physics, shows you the immediate impact.
Wow.
And it goes on. Nuclear physics is key for radiation therapy and cancer treatment. And think about MRI's magnetic resonance imaging.
Incredible diagnostic machines.
Incredible.
Yeah.
And they work based on nuclear magnetic resonance, how atomic nuclei in your body interact with magnetic fields. Pure physics. Even computational physics helps now, modeling how potential drug molecules interact in the body, speeding up drug discovery.
And things like EEG and EKG, monitoring brain and heart waves.
Absolutely, that's electromagnetism. Our bodies have electrical activity, and physics gives us the tools to measure and interpret it. It turns out we're pretty complex electrical systems.
Amazing. Okay, so medicine is clearly saturated with physics. What about, say, ICT, information and communication technologies? The digital world.
Oh, ICT is just as dependent, maybe even more fundamentally in some ways.
How so?
Well, again, optics is crucial for fiber optic cables that carry internet data at high speed. Lasers are in CD, DVD, Blu-ray players, barcode scanners.
Right.
But the absolute bedrock, semiconductor physics.
Transistors, microchips.
Exactly. Modern computing simply wouldn't exist without understanding the quantum behavior of electrons in materials like silicon. Before semiconductors, we had computers filled with vacuum tubes.
Huge, power-hungry things.
Huge, slow, unreliable by today's standards. That tiny smartphone chip in your pocket, it exists because of quantum physics discoveries.
That really puts it in perspective.
Right.
Mind-blowing, actually.
It is, and it doesn't stop there. The mechanics is involved in designing things like hard drives, how they spin, how the heads move. Electricity and magnetism are obviously fundamental for all the circuits, for storing data magnetically.
Sure.
And wireless stuff, Wi-Fi, Bluetooth, that's all applications of Maxwell's theory of the electromagnetic field generating, sending, receiving radio waves. Pure physics in action.
It's like an invisible physics infrastructure holding up our digital lives.
Yeah.
And here's a cool factoid from the source. Even HTML, the language used to build web pages, was originally developed by physicists.
Was it really? At CERN, wasn't it?
Yeah, at CERN. Just needed a way to share research documents easily. Shows how physics thinking can lead to solutions in unexpected places.
It really does. Which actually leads nicely to a challenge our source material puts forward for you, the listener.
Ooh, a challenge. Okay.
Yeah. The question is, think about any field of human activity you're interested in. Could be your job, a hobby, anything.
Okay.
And just reflect. how does it use or rely on knowledge from physics?
Hmm.
Even indirectly.
That's a good one. Makes you think.
And then the sort of playful follow-up is, can you think of any field of human endeavor that you genuinely believe has zero connection to physics?
Good luck with that one.
Right. The author kind of playfully dares you to find one and share it. Maybe in comments, if you're listening somewhere, you can do that. They'd be curious.
It's a fun challenge. Honestly, after talking through all this, it feels pretty hard to find anything completely untouched by physics, directly or indirectly.
It really does give you a new appreciation, doesn't it? For the underlying rules of the game, so to speak.
Definitely. So let's maybe try and wrap this up. We've covered quite a bit of ground in this deep dive.
We have. We looked at where the name physics came from, how it evolved, how it relates to other sciences.
Right, and those core ideas matter. Space-time. We mapped out some of the main branches, like mechanics, optics, quantum physics.
Talked about classical versus modern physics and how they fit together.
And the different ways physicists work, experiment, theory, computation, plus the difference between basic and applied research.
And then we really drove home the significance, looking at examples like medicine and ICT, showing how deeply physics is woven into other critical fields.
Yeah. So maybe the final thought for you listening is this. The next time you, put on glasses or use your phone or get an x-ray or even just see a ball roll down a hill, take a second to think about the physics making it happen. It's not just some abstract school subject. It's literally the operating system of the universe, and it quietly shapes almost everything in modern life.
Well said. We hope you keep noticing those connections, exploring them in whatever areas interest you. Thanks for joining us for this exploration.